Hi everyone, welcome to the 23rd episode of Math and Beyond Analysis podcast. I have to make a little announcement. Today probably is the last episode that I will record, at least for some period of time, which is not going to be long, but it's going to be around some month, more than a couple of months for sure, because I really need to focus now on some other aspects for graduate studies, and thus I need to spend more time and energies on these other aspects. So be sure that I will come back to the podcast and I will keep on recording episodes, but for the moment I need to take a break. Today we are talking with Sudeshna Ganguly. I hope I pronounced it correctly. She's an associate scientist at Fermilab, and we are going to talk about Muon g-2 and accelerators, her work at Fermilab, and their latest discoveries of the anomalous magnetic dipole moment that has been released by Fermilab. I will send her the invite, and I will see you shortly.
Hello.
Hi, Sudeshna.
Hey, hi, Francisco. How do you say your name?
Hi, yes, it's perfect. It's great.
Francisco? Okay.
Hi. How are you?
Good. How are you?
I'm doing fine. Yes, it's quite a bit hot here in Italy.
You were in Italy. Okay, yeah, I was about to ask you where you are at.
Yeah,
where in Italy?
I live close to Bologna.
Okay.
It's a small town on the seaside, on the eastern part of Italy, near Bologna. Yeah.
We
What
do
about
have
you?
quite a few Italian colleagues here on G-2.
Okay. Where are they from? Do you know where are they from?
INFN. So is that in Pisa?
Okay.
So some of them are from Pisa, and then
Okay.
some Rome, I think. And we visited Elba for one of our collaboration meetings in 2019.
Oh, okay.
So our G-2 collaboration meeting took place in Elba. That was quite a lot of fun.
Okay. I guess. Then what about you? Where are you?
I am at the lab right now. I'm at Fermilab.
Okay.
Right across my office in a conference room.
Okay. Thank you for sneaking up somewhere
Sure,
this conversation.
Yeah.
Okay, so I gave a small introduction about you, Sudeshna, and I said that I didn't say, you mentioned now for the first time you are part of the G-2 collaboration that recently released astonishing results with regards to the G-2 experiment, which of course we will be talking about in this conversation. So I think we can start. We can jump into it, and we had let's say sort of an outline. But I would like to ask you first a couple of questions. Let's say more personal.
Sure.
To some opinion, and I would like to ask you first. Do you believe mathematics is invented or discovered?
Mathematics is invented or discovered. Well, my personal opinion is it was found, it was discovered, it was there, and we just learned how to see it,
Okay. Okay, that's it.
What do you think?
I do tend to. Okay, so a couple of years ago, I would have said invented, because I found it more fascinating. I think it was more fascinating to have the idea that we are inventing something that we can describe than something. But then at the end of the day, studying even more physics led me to understand that actually we are not inventing something. We are just discovering the language with which stuff around us tends to work. So it's probably the least magic, let's say, the least magic of the two options, but okay. And I was, sorry, what do you want to say?
But I was going to say it's there's always fascination in discovering something, right? Always a lot of fascination involved in the process and how you reach to the result, the conclusion, whatever it is, whichever subject is it.
Absolutely. And with regards, let's say from a physical perspective, what do you think it's the most beautiful physical theory?
Most beautiful physical, you mean theory in physics?
Yeah.
Well, I mean, our standard model has been extremely annoyingly successful. It's quite annoying that it was so successful in predicting almost everything. But then there is still some hope for us because there are still some unanswered questions. By hope, I mean there is hope to discover something new. If everything has been discovered, if everything has been answered, then there won't be any fun in it, right? So, so it's kind of annoying that it has been so successful, but there are still so many unanswered questions, like why there is more matter than antimatter, what is dark matter, etc., right? So that leaves us some hope to look beyond the standard model for us, and that's what makes it so exciting for us to just continue to do these experiments, to look for these answers. And these are profound questions that we want to understand, right?
Okay. Do you believe there is a connection between Gödel incompleteness theorem in mathematics and our understanding and experimental capabilities of probing everything that we see in our universe? For example, something like space-time singularities or even the Big Bang. To me, it kind of recalls the fact that there are some questions that we very likely we will not be able to answer. As in mathematics, there are certain statements that you are not allowed to prove true or wrong.
I mean, yeah, well, I mean, it's just going to be personal opinion. What I always think that with so many unanswered questions around us, like there's so many questions we simply don't understand. Like we don't understand why what we know, their theory, why does it apply to only 5% of the matter and energy, right, in the universe? So there are so many unanswered questions till now. And so what we know, it's probably just only an approximation of a more fundamental underlying theory of nature, right? So that's all I can say. I mean, there must be something more fundamental underlying beneath what we know now. So our quest should be for that, to get to more closer to what is this more fundamental underlying theory.
Okay. Do you believe the standard, you mentioned the standard model as the most beautiful theory. Do you believe the standard model will ever be improved or maybe currently does, if it is your opinion, currently does explain or partly explain the working of consciousness and
Yeah, I mean, it has described almost everything that we perceive in the world around us, right? That's why I call it so annoying, because it has been so successful. It predicted almost all experimental results over many decades now, right? But there are some clues, some hints out there from different experimental efforts that point to the fact that there might be something out there, some new particles, some new forces that we are not aware of as of now, right?
okay. And what about the emergence of consciousness? Do you believe that the standard model may ever be able to have a try at explaining the emergence of consciousness, which at the moment seems pretty much kind of unexplainable according to our physical theories?
You mean human consciousness?
Yeah, what we perceive as yeah.
That's profound. I don't know, yeah, like how mathematically we can encompass human consciousness, right? That is a profound question. I
Okay.
don't think I'm an expert enough to comment on human consciousness, except for I'm conscious of how small I am.
That's the beauty of studying
Yeah, yeah,
physics and this kind of
right.
topic sometimes.
Right.
Okay.
So on this topic, like you just reminded me, like the consciousness that how small we are, like even running an experiment, when you're involved in an experiment, right? So when you publish your result, it's like one number, like one slide of some summary, right? But the day-to-day running of an experiment, the actual effort that goes into it, there are like so many layers, and you just are a small part of all these layers, all these activities, and you're just a tiny building block, and then everything put together, then you come to this final result, some discovery, some understanding. But then that reminds you how small we are in our day-to-day activities, our tiny little part, but that's super important. Like the tiny little part we're putting in, that is still extremely important for the final goal, to achieve the final goal, right?
Okay. Okay. And going back to the experiment you just took part in the last couple of years, first of all, what is a muon?
Oh, before, okay, yeah, that's a very good question. We will get to that. And I prepared I just like threw together some slides I had, because
Absolutely.
showing slides will be easier, just instead of like showing some pictures and diagrams will be easier instead of
Absolutely. Absolutely.
talking.
You can share your screen.
I will, yeah, I will share my screen. But before that, I wanted to say, just give you a brief introduction, like what I'm doing right now.
Mhm.
So right now I'm working at Fermilab, an associate scientist here in the target systems department. So my current project is LBNF, long baseline neutrino facility, where we're working on the beam lines, developing the beam lines and all the instruments so that we can deliver the neutrino beam to the DUNE experiment, right? So that's what I'm working now. But I have been working on the G-2 experiment, the Muon G-2 experiment, since 2015. I was a postdoctoral researcher on that experiment until 2020. So I worked like heavily, I was heavily involved with the experiment until run 2, 3, the result that you just saw recently published. So my background is in Muon, and before that, I was working on data analysis of the Bell detector, which is located in Japan, Keiki. So I switched a lot. I have a diverse background on working in these different projects and experiments, etc. So now back to Muon G-2 experiment. I will share my screen.
Sometimes I some videos I tend to hear, the muon is the heavier cousin of an election.
Yeah.
Okay, what is it supposed to mean?
Okay, let me hold on. So just give me a minute. There's so many slides in front of me. I'm not sure which one is meant for you. Okay, so I will switch back and forth between two slide decks, because I just threw together some slides. I thought that would be interesting for you. And but because you want to go back to the very beginning, what is Muon? So I will share another slide decks where I have some pictures, which will probably make more sense, to show.
Yep.
Okay, now found it. What do you see? Do you see
Yes, presentation. Yeah.
the slide? Okay. So yeah, so here we're looking at the standard model particles and the forces that control these particles, that govern them, right? So you can see the muon is sitting here. This is one of the leptons. So they're spin half particles, and I will go into that, like what that means, this actually means. So we say muons are heavier counterparts or cousins of electrons. They behave sort of similarly, but muons are more massive. And that's a good thing for us, because that makes it easier to manipulate in the experimental setup. So it's easier to use muons to look for evidence of new physics compared to electrons, because they're heavier, right? And then, so these forces, so we have these quarks and we have these leptons, and these are the forces that govern them, right? So like I have worked on muons, and now I'm working on a beamline that controls, that are going to deliver neutrino beams, right? So neutrinos are also leptons. But then what are the main differences between muons and neutrinos? Muons are charged particles, right? And neutrinos are chargeless. So because muons are charged particles, that makes them easier to use or detect. So they will interact. So muons will interact with electromagnetic forces, and then the weak force and the gravity, whereas the neutrinos will only interact with weak force and gravity, right? So if you compare them, electrons are extremely shy. So it's really, they're very notorious to be detected. They're very difficult to detect because of their weak interactions. But muons, on the other hand, they can be tracked. You can track a muon and measure the interaction when they're passing through detectors, while neutrinos are generally just passing through matters without leaving any significant trace, right? So the reason we choose muons in muon G-2 experiment for looking for new signature of physics is because they're just super easy to handle in experimental setup, and they're a very good candidate for such signature. When you're looking for a signature of new physics, they have the lifetime of muon. They have finite lifetime, about 2.2 microsecond, right? In lab frame, it's going to be larger than 2.2. So they have a very good property, these muons. They live long enough so that they can interact, but short enough so that they can decay. And when they decay to electrons, then we detect those electrons in our detectors, and I will show you some pictures, and look for the signature we are trying to look for. So they just happen to have all these right properties that we're looking for to look for this new physics in G-2, right? So that's muon. Now I will go back to the second set of slide decks where I could give you a little more insight on some more properties of muons. Okay.
Yep.
So right here. So do you see the
Yes.
slide? Okay. So I mentioned spin-high particles. So they have this property, spin. So if you just like imagine a spinning top, it's basically like a spinning top, right? So it's spinning across around an axis. And let's just like get some of the definitions out of the way first, because you will hear a lot of this mentioned in G-2 talks, like polarized beams, left-handed, right-handed particles, etc. Right? So now muons have this property, spin, right? They're spin-high particles. And you can imagine them as a spinning top. It's like highly exaggerated, but just imagine them as spinning tops. So they're rotating about their axis. So if we have particle where the spin and the momentum vectors are parallel to each other, we call them right-handed particle. And the case when they're anti-parallel, they're opposite to each other, we call them left-handed particle. So standard model tells us that the neutrinos are always left-handed and anti-neutrinos are always right-handed, right? So that's just a consequence of them being almost massless. So that's one definition. Like when we say left-handed, right-handed, this is what we mean. Parallel, anti-parallel vectors, right? And then you will here we say we get polarized beam of muon into our storage ring. In the G-2 talks, you will hear that a lot of times, that we get polarized beam of muons. That means basically all the spins are pointing in the same direction. So because of this decay, the pions are decaying in a certain way in the rest frame. They have zero momentum because they're at rest. So you have to conserve momentum and conserve spin. So the consequence of that, right? So that all the muons we get, they will come out with this signature, the left-handed, where their spin and momentum would be anti-parallel to each other. So we are just lucky that nature helps us this way, that all the muons we get, these are almost 100% polarized. They will all have the same signature, right? So these are the two definitions that I wanted to get out of the way, because you will hear them a lot of times in G-2 talks. Now, the G factor, basically. So I really like this cartoon here. That's sort of like explaining the concept. So these charged particles, they have spin, right? They have this intrinsic property, spin. They will produce a magnetic field, right? And this quantity, this magnetic moment, will have this term G in it. That's the name G-2. The G comes from this quantity. So this basically tells us the strength, how strong this moment is, or how fast the spin is going to precess if you place it in an external magnetic field. So if you place your muon, imagine this as your muon. So if you place it in an external magnetic field, how fast this is precessing? The G tells us that, right? So that's the name G. And then what is this -2 name? Where do we coin that from, right? In the name, the -2 factor. So that's basically, there's a long history starting from early, like 1920s, where experimentalists were making measurements, and then theoretical physicists were making predictions. So Dirac predicted that G should be 2 for Muon, but then later experimental values showed that it's not exactly 2, right? So then the question was, why is it not like point-like particle as predicted by theory? Is there something else going on, etc.? So that's when comes this quantum fluctuation concept, right? So the question, is vacuum truly empty? And we know that no, there are like continually many virtual particles popping in and out of existence in vacuum, right? And what's happening, so this is our muon, imagine the spinning top, and there are like virtual particles just popping in and out of existence, and they can interact with our muon, right? They can interact with our muon, and they can change their property in a way that is not predicted by a standard model. And that's where it becomes interesting. So if there are some virtual particles like these dots here, imagine those are the virtual particles. This could be known standard model particles, this could be unknown standard model particles. So they can interact with the muons and screen the magnetic field experienced by the muon, and that will change the value of G, right? So if there are quantum fluctuation, this virtual particles existed that pop in and out and they interact, then only we will have this value differing from G, right? So now the thing is, there could be known particles. These particles could be known by standard model. And there were lots of calculations and theoretical prediction done. So all these contributions, these are known contributions from all these virtual particles. And these guys here, the hadronic contributions, the most of the uncertainty comes from that. They are the dominant uncertainty in the prediction. So all these are very well known. So now the question is, so these contributions are predicted. So the prediction that you see on this plot, where you see one predicted value and one experimental value, those predicted values are coming from all these contributions that standard model knows, right? But then there could be something else that we don't know of that is beyond standard model that is also contributing to G-2, right? And if that happens, then the predicted value will not be matching up with the experiment. So if our experiment can show beyond any doubt that this is not any random fluctuation or any measurement error, if our measurement is very, very precise, and we can show that this significance difference, the discrepancy exists, that means there could be contribution from something beyond standard model that we don't know of, and that's what makes it so interesting. So I will wait if you have more questions.
Okay. What this contribution that we don't know of and that we do not predict from the standard model may be from?
So that's where I'm not a theorist, so that's where the theorists community will come together. So first they will have to prove that, yeah, we see this discrepancy beyond any doubt, that this is not from any random fluctuation. And that's where the higher the discrepancy, the sigma value is, the better the significance is, right? So we are more sure. And so our experimental result is model independent. We show that, yeah, this is a definite proof that we have new physics out there. And then theorists will come in with their predictions, the different models, and they will battle it out.
Okay. What were the last prediction about the last results that have been published?
Oh, yeah. So this is what you're seeing right now. That was from round 1, right? That was where we were at round 1 in 2021. So this number here that came from the G-2 theory initiative, there is a group. So they put together a white paper with their best prediction at that time. That was this number, right? So when we were comparing between this number and that was our experimental average after round 1, we were at 4.2 sigma, right? So now if we were at the release talk, so if you were at the release talk, you probably have seen this slide, right? So if we were to take that prediction from 2020, the best prediction at that time, the standard model prediction at that time, if we were to take that and compare our latest result, combining with the previous results, then the discrepancy will increase to 5.1 sigma. But the picture is not that clear, right? It has been muddied a little bit, and there are many layers to it now. So what happened was, so we published our result in 2021, and shortly after that, so there were some more publications that came out from the theory side. Okay, so let me show this previous slide before I get into that. Just couldn't find my mouse. Okay, yeah. So right here. Right. So the hadronic calculations that I showed, which has a dominant uncertainty in it, that's where the efforts are now being invested from the theory community, right? So there are, I'm not a theorist, so I just like understand it vaguely. So I'm just gonna explain it to you in the simplest manner, right? So there are two different ways. The dispersive calculation, where they use experimental data, right? So after they published the white paper in 2020, there were these two measurements, out of which the CMD3, that was discrepant. That was far from what the other predictions were, right? So there is that. So this is the method that was included, all those calculations using this method was included in the 2020 theory prediction, right? And that's the number we are comparing here. But later, this result came out, the CMD3 calculation, which was discrepant, right? And now there is another method, not the dispersive method, but another method, lattice QCD method, which uses supercomputer. And they solve, compute really difficult and complex equations for quark-gluon interactions in numerical methods, right? So in that way, when they're using this lattice QCD calculation, there was this new result, the BMW result, which falls somewhere here. So it falls between this and this. So there were other lattice QCD calculations before BMW, which came out, I believe, in 2021, but those were they were not that precise. So they were not that precise to compete with our experimental result. You can only compare them if the precision is comparable, right? So all those previous lattice calculation results were not precise, but this one, the BMW result, was competitive enough because in recent years, we had got more supercomputing power, etc. So using those, they were able to calculate, and that number falls somewhere here between this and this. So it's kind of muddied right now, and our theory colleagues are going to work continuously until 2025 when they predict they're going to have a better understanding about these ambiguities among their results. But then I don't think that takes away anything from us on the experimental side, because so far we have managed to produce the most precise measurement, because we're talking about ppb. And just to give you an idea of like what a ppb is, suppose you are walking hill to hill around the world 8 times like that. So one step in your journey is a ppb. So we're trying to achieve that level of precision, right? So I don't think, even if right now the picture is not that clear in terms of where the theory prediction, the standard model prediction stands, it doesn't take anything away from the experimental result because it's the most precise. And we managed to achieve the goal we've set for ourselves in the beginning of starting the experiment, you know.
Okay. Can you elaborate on the experimental setup for the Muon G-2 experiment?
Sure. I thought I will show some pictures. So I do have some slides showing the picture. So this was before I joined the experiment, when the ring was moved from BNL to Fermilab. And these were the reasons we wanted to do it again here at Fermilab. But we use the same storage ring because here we achieved we strove for more beam. We were trying to get more beam, and we tried to get better uniformity in the magnetic field and better measurement using latest technology, detectors, better calculation, different analysis methods, etc. Right? So we try to reduce our systematic errors, and that was the goal, and we reached this goal. See, 70 ppb, we reached that goal, and collect more data, 20 times, 21 times more data, right? So yeah, so all those runs have been completed, and we just ended our experiment this July, I think early July, 7th or 8th of July, yeah. And so far we collected so much data, see, 20 petabyte of data and 100 million CPU hours to reconstruct, analyze, etc., etc. Right, so it has been like an immense effort. So this is how it starts. So we have in the accelerator complex, we have a recycler ring from where we get the AGV protons. And then we bring the protons, smash it into this target, which produces the pions. Then we focus the pions, right? And we send them in a dedicated path where the pions can decay. So the pions are decaying, and then they enter into this delivery ring, which acts like a filter. So it filters out whatever unnecessary particles we don't want. It filters out the protons, they're kicked out. So whatever comes out of the delivery ring is muon, it's muon beam. So we get, like I said, polarized muon beam out of this delivery ring, right? And that happens from the pion decay. So this delivery ring acts as a filter. It gives us the muon beam. And then we send it to our experimental hall here. It enters through here. We provide another path for the muon beams to come in. And then it enters our storage ring. But when it enters, it's not correctly on the right orbit. So you can see it's kind of shifted. It's not falling on the right orbit, right? So we have to move it properly. You have to fit it properly within the storage ring. So for that, around like 3 o'clock location here, we have a kicker magnet, which gives it a kick. And after giving it a kick, so from the black dotted line, it becomes the rightly orbited beam, right? So now it's in the storage ring, it's properly orbited, but we haven't focused it vertically. So we don't want any muon beam losing from top or bottom. So we have this electrostatic quadrupoles in these 4 different locations, which provides us squeezing in the vertical direction like that. So we contain our beam, right? So all these subsystems are extremely important. The kickers, the quads, the actual storage ring. And yeah, so that's like cross-section of the storage ring. So we need to maintain the uniformity of the magnetic field very, very precisely. That will go into our final calculation, right? So that is a slice of the storage ring itself, and then the calorimeters. So we have 24 calorimeters. You can see all these boxes all around the ring. There's just sprinkled all around the ring within the inner radius, 24 of them. So they're crystal calorimeters. They have lead fluoride crystals, right? So these calorimeters are what gonna detect the decay positrons from the muons, right? So why do we use decay positron? Again, we have been lucky. The decay positron carries the information of the parent muon. They carries the same spin information of the parent muon. So from them we can infer the spin direction of the muons, and that's what we want to measure. But the daughter positron, decay positron, carries that signature. So we're lucky again. And that's what we detect, the decay positrons in our detectors, in our calorimeters, right? So what happens is the highest energy positrons, they will have the strongest. So so this is the highest energy, right? So if it's a high energy positron, so their momentum and spin will have a correlation, the strongest correlation, right? And when it's the lowest, they're backwards, the lowest correlation, and somewhere in between. So again, we have this correlation between the energy and the direction of the spin, and we utilize that in our calorimeter. So what we do is we choose those high energy decay positrons, and by doing that, we are able to see this oscillation, and that goes into the wiggle plot that you will see. So G-2, you will always see this wiggle plot, and this is basically the wiggle plot. And in the result talk, you saw like lots of sources of systematics, but that's a lot more detail. I'm not going to go into all that. But in the simplest form, you can just fit it with this 5-parameter fit in the simplest form in ideal life. But actually, real life is not that ideal. So there will be lots of systematic uncertainties. So we take care of that. But basically, you just want to get the wiggle and fit it and extract omega A, right? So that's like the simple possible way to explain how we extract omega A. But of course, in reality, there will be a lot more complications and systematics associated to that. And this omega A will go finally into the calculation of the A mu, or the magnetic anomaly, which basically tells us how the quantity G differs from 2 fractionally, right? And the G factor is basically telling us how fast the spin is processing when you place it in an external magnetic field, right? And if there is some unknown particle interacting with muon in a way that we don't know of, that is probably changing the value of G. That's where new physics comes in. That's where beyond standard model physics comes in.
Okay. What are your not expectation, but let's say, what are your projection for the next years of Muon G-2 experiment and collaboration?
So yeah, so I think I do have a slide showing where we're gonna be at. Yeah, so see here, run 1, we analyzed about less than 5%, just about 5% of the data, less than 6%, 5% of the data. So run 2 and 3, now we doubled the statistics, right? But we have 3 more runs. So we've collected data over 3 more runs. So when we finish analyzing the data from those 3 runs over the next few years, it's going to be 4 times more statistics than what we had, right? So we expect the statistical uncertainty to go down by another factor of 2 or so. So we should be able to reach our projected goal in terms of what precision we wanted to achieve. And we have, so right now I'm not actively working on, I worked on G-2 until run 3. I was one of the run coordinators and then briefly acted as operations manager before I moved on to this position. So I'm not involved in 4, 5, 6, but our grad students, we have many grad students and postdoc who are diligently looking at the data, analyzing the data, and coming up with, say, more creative ways to make it faster, the processing, the analysis, etc. So they're going to be working diligently on that. And so by the time the theory community will try to answer their ambiguity, we should be, again, be able to ready with the run 4, 5, 6 results combined, you know.
Okay. Okay. Sudeshna, you have also been the run coordinator of the Accelerator division. I would like to ask you some question about why are accelerators so much important for probing new physics, and nowadays why actually some couple of years ago there was some hype for the accelerator at CERN. Why are accelerator a useful tool for physics?
Well, yeah, accelerators, we absolutely need accelerators. So at Fermilab, we operate the largest accelerator complex in the US. So in my mind, there are 3 main reasons the complex is extremely important. So we need accelerators to deliver beam for performing research for the experiments that are running right now, right? That's one reason. Then we need to conduct accelerator research in the field itself. We need to continuously look for advanced ideas, concepts, technologies, right? So we need to move this field itself forward. And we always should challenge ourselves and need to upgrade our complex, our accelerators, beamlines, targets, so that we can extend the scientific reach, so that we can discover new physics, right? Beyond what is running right now, we should always be in the lookout for something new and push ourselves. So something like that we're trying here right now. Fermilab is going through the process. So have you heard of PIP2, which is PIP2 is Proton Improvement Plan 2, right? So Fermilab has undertaken this project, PIP2. So the plan is to modernize our accelerator complex, right? So we have this linear accelerator, and these are old machines. So we're going to replace this linear accelerator with the modern new accelerator, where we will have superconducting RF cavities. So we're going to use new technologies, right? And the aim is to increase the beam power. So right now, the the linear accelerator, provides us 400 MeV beam power, and this new PIP2 LINAC will be able to give us 800 MeV beam power. And why do we want to do that? Because we want to deliver higher power, higher intensity neutrino beam to DUNE. The planned initial beam power is 1.2 megawatt, and then we want to go to 2.4 megawatt in phase 2, right? So to be able to do that, we'll have to improve our complex itself. And we'll have to use latest technologies like superconducting cavities, because we want to be efficient, we want to be cost effective, we have to be cost effective because this is a huge campus, right? And then we'll have to like look for future experiments where we can have more beam, more protons, and so that will open up avenues for more experiments, and not just DUNE. So DUNE can run concurrently with these upgrades in the accelerator. This will allow the campus to run many experiments concurrently. So after G-2, we're going to have Mu2E in Muon campus. But under PIP2 era, we will be able to run another experiment. Like, it is not confirmed yet, so it could be anything. But I'm just saying as an example that concurrently with DUNE, we can run an experiment like Mu2E2. Right, so this will give us the flexibility to run multiple experiments at the same time. So for that itself, it's super important to continuously try to improve the complex, you know.
Mm-hmm. And what about if you can explain what are the, let's say, key components and technologies that are composing the accelerator
complex? Sure. Okay, let me show you a picture again. Right here. Yeah, so do you see?
Yep.
Okay, so this is basically a cartoon showing our accelerator complex. So this is the main complex, right? It comprises of particle accelerators and storage rings. So we have the linear accelerator. You see, it says LINAC. So LINAC is a linear accelerator. So that ramps up the proton beam energy to 400 MeV. So then after LINAC sends the beam to the booster. So the booster, the circular ring that you see in the cartoon, that's booster. So that ramps up the energy to 8 GeV, right? So then from booster, we can take those beam and we provide this low energy neutrino beam to our short baseline programs. So we take the beam directly from booster and send it to the short baseline programs to their targets, right? Now the booster sends the beam to, you see, main injector. So main injector, above that ring, we have another ring, we call it recycler. It's just sitting on top of main injector. So from booster, we take the beam and we send to recycler, where we combine the beam, and the combination is called a batch. So you form batches of beams, right? So then those batches are then sent to main injector, where they're accelerated again, right? And this time from 8 GeV to 120 GeV in main injector. And those 120 GeV protons are now currently being sent to new me beam lines, neutrinos at main injector. And in future, those being the 120 GeV proton beam will be sent to the LBNF beam line and the target. So new me is the current experiment, that is NOVA is the experiment, new me is the beam line that is currently running. So we send the 120 GeV proton beam to them, right? Now in recycler, from booster, we got the 8 GeV proton beam recycler. And we use those 8 GeV beam directly for the Muon campus. I showed you the picture where we take the 8 GeV proton beam and smash it into a target to create muons for G-2. So that is the Muon campus. So we also use the 8 GeV beam directly from recycler before sending them to main injector for the Muon campus. And then also we have test beam facilities, which is super important, where we take the 120 GeV proton beam, send them down another line, and send them to users, multiple users at the same time. So the test beam facility is basically, and that's called switchyard on the picture. So it's basically where users come with the detectors and they can use our beam time to perform various R&D efforts, you know. So that's where the campus is. And this LINAC will be replaced by the new LINAC under PIP2. And then we are currently working on the long baseline beam line designs and instrumentations, performing prototype tests for various monitors, etc. So all those activities have started already.
Okay. And what, let's say, which experiments fell under your supervision at Fermilab?
Okay, so right now the department I work in is called Target Systems Department. So the primary goal of the department is to come up with high power targetry. And this is super important, you know, so the high power targets are going to be a bottleneck if you are not ready for this future high power experiments. The current technology allows us to go as high as 1 megawatt beam power. So to go to 1.2 and then in future, say 2 megawatts or more, we need new target materials, right? So lots of engineers in our department, they are continuously working on finding these materials for high power target operations, not just for target, for like beam windows. We need like these targets for these materials for various beamline components. They will have to withstand this increased radiation, you know, radiation dose. So those are the like primary goals of our department, but not just that. Like I don't personally work on targets, but I work on beam lines. So we are also in charge of developing beam lines, which will take the beam, create the beam, like smash the proton onto a target and create the beam down this beam line and send it to the user. So we are in charge of the LBNF beam line, and we also work on the Mu2E beam line. So all the upcoming projects, we're working on that. And hopefully in time, we should be able to deliver beam to them.
Okay. What are the most frequent challenges that you face? Let's say both technical and non-technical challenges.
I can, I guess, tell you a little bit about when I was a run coordinator in the Accelerator division. So I actually worked as a run coordinator on G-2 in 2019. And then afterwards, in 2021, I was a run coordinator of the whole accelerator complex, right? So the difference was when I was a run coordinator of G-2, that's just a small experiment in compared to the whole lab, right? Versus when I became an run coordinator for accelerator complex, I had to take care of all the experiments running, all the machines, and a lot more coordination. To put it in the simplest form, a lot more coordination among various groups. And the whole thing happened. I was in charge when it was COVID, so we were still working remotely for most of the time. So technically, if something would break, and machines break every now and then, right? But our goal is to try to deliver beam as efficiently as possible without impacting the experiments, right? So it was very challenging to get people with all the safety protocols, adhering to all safety protocols, because before we can just stop by our colleague's office and do some brainstorming. But now you would have to make appointment, think about safety, and suppose something breaks in a high radiological area, then we'll have to work with the safety office, radiation safety office, etc. So doing all that remotely, you can imagine how difficult that could be. And it's just not one experiment. Now you're running trying to send beam to all different experiments and all facilities, and it's 24/7 and COVID. So it's like a combination of both technical and human challenges, you know.
Okay. What about instead your work, the work at Fermilab you do at DUNE, and why is it related? Let's say, what are the purposes of this work? With
You mean the DUNE science goals, etc.?
Yep.
Right. So, okay. So even though currently I'm mostly working on the beamline, which is the long baseline neutrino facility, but I'm also part of the DUNE collaboration. So the DUNE collaboration is deep underground neutrino experiment. So that's going to be the experiment. And LBNF will be the infrastructure to send the beam to the experiment, you know. So my current work is mostly involved on the beamline side, but I'm also like pursuing some of my personal ideas of doing simulation, etc. So the basic physics goal of DUNE, like the main physics goal of DUNE, they have many goals, of course. The primary goals is to precisely measure the properties of neutron oscillation, right? And specifically the mixing angles and the ordering of the neutrino mass eigenstates, etc. So that's a crucial step. If we can do that, that's going to be a crucial step in understanding the fundamental nature of neutrinos and the interactions, right? But not just that. So DUNE has many primary goals, and that is one of them, what I just mentioned, like precisely measure the properties of oscillation, neutron oscillation. But they're very, very interested. DUNE is very, very interested in looking for signatures beyond standard model physics. So they want to investigate whether neutrinos and antineutrinos behave differently under the charge parity symmetry violation. So this could explain why our universe has more matter than antimatter. So that's one of their goals. Proton decay search. So DUNE also has the potential to search for proton decay. That's going to be a hypothetical process where proton, which is a stable particle, decays into lighter particles, right? So that would be significant if we can observe proton decay via DUNE, because that's in a way challenge our understanding of the stability of matter, and the conservation of barrier number. So yeah, so DUNE has many physics goals, and currently I'm focusing on working on the beam line, which would be able to deliver them the beam so that they can continue to look for all this amazing physics,
Mhm. And how does DUNE detectors capture and analyze neutrino oscillation?
DUNE detectors, yeah. So, well, these are based on liquid argon, a large EPC time projection chamber. So I don't work on the detectors directly, but I can just give you a brief summary. So what happens is neutron interacts with the liquid argon. It produces charged particles, and the detector will have electric fields within it. So the electric field will cause these charged particles to ionize the argon atoms, right? And when the argon atoms are ionized, they're gonna free electrons and ions. So then the electrons are gonna drift towards an anode plane where they will create a signal, and this will be recorded. The signal will be recorded by readout electronics. And by analyzing the signal, physicists then will be able to reconstruct the path and the energies of the interactions of the particles. So that way they will be able to study neutrino properties and interactions. So that's the near detector, which will be located here at Fermilab, but you'll have a massive far detector. I think it's about 1,300 kilometers, if I'm not mixing up the unit. Yeah, like away from Fermilab underground in South Dakota. In their facility, they will have a far detector, which will be technologically the same, liquid argon time projection chamber. But it will be put underground, and it'll be very large so that it can cover a wide range of energy, and the long path that will allow us to see if neutrino changes its type. So that's the oscillation. It changes identity. So when it starts to when it reaches the detector underground, if it changes the type, then that will be a signature of oscillation.
Okay. Let's say, why is it important to study these properties?
Well, I mean, we're always constantly looking for a signature of new physics, right? So there are two different ways. So say the way CERN does it. Collide particles, smash atoms into each other, create new particles. They're really high energy particles and look for signature in their data. So that's a direct search for new physics. What we're doing here, we're looking for indirect hints of new physics by creating high intensity, high precision experiments, right? So it could be possible that the new physics, where it lies, it could be outside the reach of CERN, outside the reach of LHC. It could be so large that it's just outside the reach of their detector, right? So it's always good to have direct and indirect ways both to look for new physics. And what we're doing here is an indirect way to look for signatures of new physics, just by creating high intensity, high precision experiments or measurements.
Okay. You mentioned previously proton decay, but why do we search signals of proton decay at DUNE?
Well, I mean, DUNE has the potential to look for this signature, and if we see a signature like that, that's going to be that's going to challenge our understanding. So the conservation of barrier number, that's the fundamental symmetry in standard model. And if we see proton decays, that's going to challenge that, right? And one of the grand goals of particle physics is to unify the fundamental forces of nature, right? So standard model very successfully describes three of the fundamental forces: electromagnetic, weak, and strong forces, but it does not include gravity. So unification of the forces is a central theme, right, in theoretical particle physics. So if we can observe proton decay, that could provide evidence for such unification theories beyond standard model, right? So, but even if proton decay is not observed in DUNE data, uh, the if proton decay is not observed, and experiments like DUNE still can set a very stringent limit on the lifetime, right, on the proton's lifetime. So there will be a lot of value in that itself. But the highlights, like why is it going to be possible for them, right? So the always a challenge in neutrino experiment is distinguishing neutrino interactions from background noise and other particles. And neutrinos are so very elusive, right? They're very shy particles, so they interact very weakly with matter. So we have a large volume of material in the DUNE fire detector, and that's the reason, because we want to increase the likelihood of capturing interactions. And the massive detector helps reduce the background impact, right? Because we are now increasing statistical significance by just creating a huge, ginormous volume. So that way, it's going to be a flagship experiment when it's done.
Okay. And Sudeshna, well, when you study this or you're working on these experiments and you are trying to probe new physics, thus new theories that may be better at explaining our physical reality, what do you think? And I know that you are an experimentalist and not a theorist, but what do you think the meaning of this all is? Why is everything so complicated, but at the same time also apparently fine-tuned for complex system as us to arise, and we really don't know whether we are the most complex systems there actually are, or that may ever emerge in our
We're always like on the brink of um we think we're on the brink of understanding everything, and then we realize that there might be something underlying. We're not really seeing the full picture. I mean, there's not an easy answer to that, like why why is that so, right? All we can do is try, and that's why there are so many different experiments. They're trying different ways. Like, for example, I just mentioned LHC, trying in direct way, or high intensity experiments. We are trying another way. So yeah, so I mean, there's not an easy answer to why we cannot quite grasp it. All we can do is continue to try our efforts and develop all these new experiments. So for example, like I said, LHC and other high intensity experiments will look for discrepancies, will investigate discrepancies in their data, right? But g-2 itself will analyze their own data beyond just calculating a mu, and they will look for new physics as well. So our grad students are working on, say, charge parity time reversal and Lorentz symmetry and dark matter searches within g-2 data itself. But again, that's just a like trying to solve one tiny problem, but it itself is so difficult. So there's not a single answer to say, yeah, now we understand everything and how everything is, all the forces are unified. There's no simple answer. So we're just continue to try and strive to do the best we can.
That's the only option we have available.
Yeah. We just have to
Okay.
find different ways and be creative.
Okay, Sudeshna, thank you very much for your time and your explanation. I will leave you go. So I think we can wrap it up here, our episode.
Thank
Thanks
you.
again, Sudeshna.
Thanks so much. That was fun.
Congratulations for the last results. And yeah, Thanks everyone
Of course,
for
it was fun talking to you.
great. I'm
Okay.
happy about it. Thanks everyone for following along with us. I will see you in the next episode.
Bye.
Bye.